It is a pleasure for us to start the last session of the conference with Eero Simoncelli. He's a Silver Professor of Neuroscience, Mathematics, Psychology, and Data Science at New York University, and he has this prestigious position of a Howard Hughes investigator. So thank you so much for coming to Deep Math.
Thank you, Soledad, and thank you for inviting me. I've only been able to hear little bits of the meeting because I have too many things to do in the last 2 days, but it's been really fun and I'm enjoying it a lot. Okay, I'm gonna, excuse me? Are we good?
Good.
Okay, cool. I'm gonna work we've been doing on denoising. And the purpose is not actually to talk about denoising. Denoising is maybe seems like a somewhat mundane, even a boring topic. And I'm hoping that I'm going to convince you otherwise, because the point of the work is really not the denoising itself, although that is a valid application. Our interest in this is really to use denoising as a tool, as a window to understand images, to understand representations of images, and as I'll focus on for today's talk, to understand something about prior distributions of images. So what's the problem of denoising? You've taken a photographic image, set of pixels of intensity, they could be grayscale or color, and you corrupt them in some way. And the purpose of or the goal of denoising is, of course, to remove the corruption. And it's worth pointing out that this is something that's very intuitive and natural, I think, to think about, because in a sense, your visual system is already aware of this problem. If I were to show you those two images, the X, the original image, and the Y, the noisy observation, you would immediately know that there's something wrong with Y. You would see that there's something not right about it. And you might ask yourself, well, how do you know? How does your visual system know? Your visual system knows the difference between noise and signal. Your visual system is able to some extent to eliminate the effects of noise, to see through the noise. And in a sense, what we're trying to do when we denoise images is, from my perspective, because at least half of my work is really about computational neuroscience and understanding how the brain processes images, I'm interested in understanding a bit about how your brain might do that and how we might do that with an artificial system. Okay. I want to just start with the completely classic view that comes from statistics, and I'm going to refer to that as a Bayesian view. And because everything I'm going to show you is kind of built around this. And the idea is very simple. If you want to know what the best estimate is of the original image, given this noisy observation, the answer, according to Bayesian reasoning, and by the way, and if you assume a loss function, which is squared error, the answer is to take the conditional mean of the posterior. And that's written here. Can you see my pointer? Yeah, okay. So X hat of Y is going to be the estimate, or the denoised image, if you like. And what we're looking for is to minimize, to solve an optimization problem, which is to minimize the expected squared error under this posterior. And all of this is presumably familiar to you. And I'm going to basically, this equation is a starting point for where I'm going to go later in the talk. So I wanted to initiate you to it in the very beginning. Okay, so the question is, to do this in this sort of traditional mindset requires that we know really two things. We have to know something about the measurement process, the noise, if you like, the corruption. And that's expressed in terms of this conditional of P of Y given X. And in a simple case, that's just basically the distribution of the noise. If we imagine additive noise, then this is just the distribution of the noise evaluated at Y minus X. And the other piece that we need is, of course, a prior model, which is some description of the signal itself, which we need to be aware of before we've even seen this noisy observation. Okay, so that's a sort of traditional view. And the traditional view says that you have to come up with a description of those two things, and you put them together, and you crank through this formula. Maybe you get a closed form answer. Maybe you do it with some numerical approximation, but in the end, that's what you're doing. You work forward from those two components, the signal model, the prior model, and the measurement model, and that gives you a means of doing least squares optimal estimation or denoising. Okay. And of course, denoising, like essentially every application in image processing and in many other fields, has been completely modernized and revolutionized by the advent of deep neural networks. I think there's no refuting that anymore. In the beginning, many of us were resistant. We said, no, this can't be. It doesn't make any sense. But I think the truth is that the results are astounding. And if you train a denoiser, a deep neural network, on this problem, in a supervised fashion. So you're going to hand it pairs of noise. You take original images, you corrupt them with fake noise, and you train this in a supervised fashion. It's a nonlinear regression problem. It turns out that you can get incredible, state-of-the-art results. And in fact, what's on this slide is such a result. This image was denoised using a deep neural network. Okay, so my goal in this talk is not to focus so much on the denoising itself, but to think about, so the forward version of the problem is that you need a measurement model and you need a prior, and that gives you a denoiser. What I want to think about is to work in reverse. So it's very difficult to build prior models on images, and I'll say a little bit about that in a minute. And that's because the space is huge. And we can't do it by building histograms, obviously, because it's a high dimensional space. Cursive dimensionality is going to keep us from doing that. So we need some sort of either parametric form or a bunch of conditions or symmetry properties, invariances, et cetera, in order to come up with some prior model. And people have been doing that, of course, for many, many decades, really going back to the 1950s. And they've had a certain amount of success, but nothing really comes close to what can be achieved with these CNNs. So what's changed is that the CNN, rather than trying to build a model for the prior, builds a model for the denoiser directly. That is, we estimate the mapping itself, and that's parameterized in some architecture using convolutions and rectifiers or other sigmoidal kinds of nonlinearities. And the amazing thing is that machine learning and basically, like I said before, nonlinear regression allows us to come up with incredible answers to this problem. So my task for today is to try to think about, first of all, if you learn such a denoiser, what are the properties of the mapping that's been learned? What can we do to analyze that? And then working backwards from that, what does that tell us about effectively the implicit prior? So if you have one of these mappings and you are thinking about it from that Bayesian standpoint that I just described, effectively it has built into it a prior, an understanding of what images are supposed to look like and what images are not supposed to look like. Just like your brain does, as I was saying earlier, your visual system knows what an image is supposed to look like, and it knows when there are artifacts in an image. So the question is, how do we work backwards? If I have a mapping for doing denoising and I've managed to learn that from a lot of data, how do I go backwards and figure out what the implicit prior is? And of course, not only do I want to know roughly what are the properties of that prior, but I want to be able to use that prior to solve other problems. So I'm going to basically walk you through our attempts to do this. This is ongoing work, and it's very recent work with the folks that I forgot to mention by name on my introductory slide. There were two fantastic students, Shreyas Mohan and Zara Katgodai, are both data science students working on this problem jointly with myself and Carlos Fernandez Granda. And Carlos is a faculty in math and data science at NYU. Okay, so that's my goal, to try to probe these three questions. So let's get started. I want to start by just reminding you, one of the ways we can get some insights in how to do this is to look back at the classic solutions and think about what the relationships are there between the prior model and the resulting denoising function. And so if we look at the very simplest case of additive white Gaussian noise, here's our signal X. We corrupt it by adding Gaussian white noise. with, this is sort of independent, and it's got, I'm just doing the scalar case here. So it's just got a standard deviation of sigma z, and we observe y. And a few things to note, what's called the prior predictive density, the distribution of y, the noisy observations, is related to the original density p of x in the following way. It basically, because this is additive, this turns into just a convolution. And in fact, it's a convolution with a Gaussian. So that's what you can see in there. That's because of the Gaussian noise. So in fact, the prior predictive density in this case, P of y, is just a blurred version of the prior. And that's going to turn out to be important later on. So I'm just trying to mention it up front. So that's a simple observation. And let's, given this setup of additive white Gaussian noise, let's look at a couple of examples. So the classic example, of course, that goes back to the 1950s is to assume that the distribution of the signal itself is Gaussian. In that case, you get a linear estimator, and you get it in closed form, and it's completely straightforward. I'm sure all of you have seen this before. It's also the solution to the, you can think of it as a solution to the regression problem, linear regression problem. And the solution, the way to think about this solution intuitively is that you take your distribution, your prior distribution, P of x, you add noise, now you have P of y, which has a variance which is larger than the original signal variance. And that's just because you've added two independent random variables. So the variances add. So we now have a variance which is sigma x squared plus sigma z squared. And what you have to do to denoise is basically squeeze it back. So the distribution is expanded and you want to push it back. And the way you do that is by just multiplying by a constant, which is between 0 and 1. And whether it's 0 or 1 or somewhere in between depends on how strong the signal is compared to the noise, okay? And this is of course, very well understood and has been used since, as I said, really the 1940s. Norbert Wiener came up with a way to describe this and to do it in a multidimensional space, and described it in the context of stationary processes. So when we go to the multidimensional problem, if you've got a joint Gaussian source, what you do, but you're adding independent white Gaussian noise, what you do is, if you assume translation invariance, stationarity, then you know that you can diagonalize the covariance matrix by doing a Fourier transform. So you do a Fourier transform, and then you solve the scalar problem for each of the frequency components. And so, and that essentially is the Wiener filter. Because this is basically just multiplying by a scale factor in each of the frequency components, the entire thing is a linear operation. And because it's a linear operation that's essentially a multiplication in the frequency domain, we can think of the convolution theorem and flip this back into the spatial domain and note that the end result is just a low-pass filter. That is, the denoised pixels, the pixels that we get out of the denoiser, each one of them is simply a weighted combination of its neighbors. And the weighting is determined by these scale factors that are in the middle of the diagram. Okay, so this is just a pictorial description of things that I assume that most people are very well familiar with. But what I want to emphasize is sort of two things. One, there's this idea of shrinkage. So adding the noise expanded the density, it broadened it, and we want to push it back. So that's one concept. So all of these multiplicative factors are between 0 and 1. The second point is that any aspect of signal that's small variance, is essentially going to be set to 0. And so we can think about this approximately, or at least in the case where the noise is overwhelming some pieces of the signal, as a projection into a low-dimensional space. And the dimensionality of that space will depend on exactly how many frequency components are being discarded or approximately discarded. So we can think about this as a projection, a linear projection. Approximately. Okay, and that takes us to sort of the next stage in the evolution of this stuff, which is a little bit, it came as a big shock, really, a surprise. Starting in the 80s, people noticed that for photographic images and for actually many other signals, bandpass filter responses are not Gaussian. So what's shown here is a probability, it's basically a histogram, but it's over many images. Bandpass filtered images, gather up the responses of that come out of the bandpass filter, build a histogram, plot the essentially the probability, but this is a log plot. And so just to emphasize the point, the dark line is the probability that's observed empirically, and the dashed line is what you would get if things were Gaussian. It's an inverted parabola because, again, this is log probability that's plotted here. And so a Gaussian would turn into an inverse parabola. So what you can see is that the density is much, much sharper than a Gaussian. It has a very sharp peak in the center. It's got heavier tails, et cetera. And this has, again, been known for a long time, but it was a bit of a surprise when it was first observed, because of course what this means is that these signals are not Gaussian, and that entire Wiener approach, the entire everything that was built up previously, is a very crude approximation. If you find any slice of a Gaussian that's not, any slice of a distribution that's not Gaussian, that means the density is not Gaussian. It's not jointly Gaussian. Okay, so now just go and plug in to exactly the same infrastructure. I'm still assuming, just to emphasize, I'm still assuming additive white Gaussian noise, and I'm still assuming that I'm trying to minimize squared error. So those two aspects of the problem have not changed at all. The only thing that changed is the prior, the distribution, and I'm now going to assume a prior that's heavy-tailed. In particular, for the examples on this page, let's just take a prior that a distribution. Whoops, I've mislabeled this. This should be P of X. The prior distribution is an exponential in X over S raised to a power P. If P was 2, this would be the Gaussian case. If P is 1, it's a Laplacian. If P is a half, it's something else. All of these are called by various names, but one of them is stretched exponential or generalized Gaussian. And the key point is that when you go through turning the crank, even just numerically, to figure out, well, what's the optimal solution in these cases, it's no longer linear. Again, the Gaussian case, P equals 2, is linear, but the case of P equals 1, the Laplacian case, actually looks like something which is to subtract off a constant in the extremes, out in the tails, and or to add a constant on the other side, anti-symmetrically, and to do something that's a little bit suppressive, that is compressive in the center. And if we go to an even heavier tailed case like P equals 0.5, this is a very heavy tailed distribution. You get something that looks like it preserves things out in the tail, but it basically discards things near the center. And you can calculate, these are calculated numerically from a paper that I wrote with Ted Adelson back in the mid-90s. But the point is that it's something a little bit jarring that even though we're assuming Gaussian noise, and even though we're assuming squared error, the estimator is, people often think that as soon as you've got Gaussian noise and squared error, the answer must be just the linear answer, but it's not. This is a nonlinear function that you apply, a shrinkage operator that you apply to the data. It's easier to think about these in a sort of, if we describe these functions as thresholding functions, you can sort of look at them as thresholding functions, but they're smooth and soft. And of course, if you switch to these, you can think of these again as sort of extremized versions of the P equals 1 and the P equals a half case, a soft threshold and a hard threshold. And of course, these were popularized and made very famous by David Donahoe's work, showing that you could effectively get near optimal shrinkage out of functions like these if you could choose the thresholds correctly and adaptively. Okay, so the key point here that comes out of all of this is that these things are kind of like in the Gaussian case, they're doing shrinkage, but the shrinkage now is adaptive in the sense that you look at the actual values of the coefficients and you only do the shrinkage, you only throw them away if they're small. In the smooth case, that sort of happens gradually. So look at this P equals 0.5 case. You preserve very large coefficients or nearly preserve them, and the small coefficients you suppress. You don't quite push them to 0, you just suppress them, shrink them. And in this more extreme case of a hard threshold, you actually pick a threshold. Everything smaller than the threshold is set to 0, everything larger is left alone. So the idea again is that what's going to happen in this situation is you're actually doing a projection. You're projecting all the values that are small, that are near your axis, are going to get discarded, and everything else you're going to preserve. And of course, when we put that together in a whole transform in order to denoise images, we have what are usually called, wavelet shrinkage solutions. So the idea is you take your image, you run it through a bunch of bandpass filters, and together those form a transform, often an orthogonal transform or maybe a tight frame. And then inside of the transform domain, you do this shrinkage. You do this some sort of a thresholding like shrinkage, which is really an adaptive, you can think of it as an adaptive projection. And then we come back out, and that gives us our denoised results. Okay, so in both cases, you're doing some sort of, it's shrinkage, but it's a specific thing where you're really doing something like a projection. And again, the reason I'm bringing these up is because we're going to look for these things in the deep net. Okay, so let's go ahead and do that. So here's an example of a deep net. This is from a 2017 paper. At the time, it was state of the art. Everything I'm going to tell you about works for all the deep nets we've tried it on. There are 4 examples in the code that we've released online. So you presumably, and the code is pretty general, so it's not hard to run it on different examples. Okay, so and this I'm going to refer to this as DNCNN from this paper. It's a very standard architecture. It's 20 layers. Each layer has 64 channels. There are 3x3 filters. They're using batch norms, so additive constants, and then rectified linear nonlinearities. There are about 700,000 parameters that are basically the convolution kernels, all those little 3x3 kernels, and the additive constants that go with them. And this is trained on the Berkeley image data set. So you take lots and lots of images out of that data set, and you add noise to them, whatever level of noise you're training on. Usually we're going to train on a range of noise levels. That's going to be a key point in just a moment. And you do regression. You solve for the best theta for minimizing squared error. Okay, so remember that my point is that once you've trained that CNN, so we have now f of theta hat, where theta hat is the optimal theta over the training set. What I want to know is, what are the properties of that mapping? How can we interpret that as being related to some sort of prior? And moreover, can we use that prior that's embedded in that denoising network for other purposes? Okay, so let me walk you through those things. First, let's think about the analysis. So we started out by training this thing on a wide range of noise levels. I'm going to show you these plots that are input PSNR versus output PSNR as a function of input PSNR. PSNR is, of course, the log of the signal to noise ratio, and so, or the log of the ratio of the variances. And so bigger is better, just to be clear. So a big PSNR is a small amount of noise, and vice versa. So what's shown here is a plot showing the comparison between the two. The dashed line is the identity, and the black line is what you get with a Wiener filter, and the red line is what comes out of this DNCNN after it's been trained over this entire range. The blue band that's shown here is the training range. And you can see that it's much, much better than the Wiener filter. These are pretty substantial gains. And in fact, visually, it looks really good. There's the same example that I showed you on the previous slides is down at the bottom here. There's a noisy test image. It's a pretty high level of noise, and there's the denoised version of it. Okay, so that everything looks great. And by the way, I should say before I jump ahead, that one of the things that's surprising here, that's already different than all the previous sort of traditional approaches, is this thing is universal. It operates on any noise level. You just hand it an image and it knows how to remove the noise, whether it's a little noise or a lot of noise, it knows. And so that's already an impressive feat. Okay, so the question is, can it generalize? And in particular, if you train it on a small amount of noise, can it generalize to larger amounts of noise, or vice versa? And the answer is not really. So here is, it's the same plot, but now we've trained this network, again, over the blue range. So we've trained it on a smaller range of noise. These are smaller levels of noise. And what you can see is that the performance is excellent inside the training range. It basically looks like it did over here. But once you get outside of the training range, it plummets. And in fact, it plummets really quite dramatically to the point where the behavior over here is worse than the Wiener filter. And I don't know how well you can see it on the slide, but here's an example it's the same example that's shown in the left plot. but now you can see that the denoised image doesn't look very good. And in fact, if you go far enough away, you can get, well, anyway, you get the point. And in fact, we can do this even more extremely. So there you see an example. Sorry, I'm trying to figure out how to hide my camera view so it's not blocking my slide. Okay, so on the right, you see an extreme example where the training is only over a very tiny amount of noise, barely visible. And now we're testing on a very noisy image and it looks terrible. The denoising performance is absolutely terrible. You can see that in the plot. Okay, so what's going on? Why is it able to generalize so well when you train it on the whole range, but it just falls apart completely when you train it on a narrower range? And we were a bit puzzled by this, but we started thinking about it and we came to the following realization. We tried to analyze what was going on and we said, well, wait a second, each stage of this is doing a linear convolution, it's adding some constants, so it's really an affine transformation, not a linear transformation. It's affine. And then we're going through the ReLU, which is just basically a rectifier, half-wave rectifier. So what that means, as Rich Baranio pointed out yesterday, is that this thing is, in the end, the whole thing is affine, but conditioned on that binary choice of whether your rectifier is turned on or not. Okay, so in other words, it's sort of like you're multiplying by a binary value, a 0 or a 1, based on the sign of the output, but otherwise, the whole thing is affine, because if you multiply by 0, that's fine. If you multiply by 1, that's fine. So this thing conditioned on the settings of all of the ReLUs, each stage is doing something affine. And moreover, when you cascade them, of course, it's a cascade of affine transformations. Each one of them is adaptive in this sense of the choices of the activations, the rectifiers. The entire thing is affine. So we can write this function f of y that this network is computing as a matrix a sub y of y, and it's explicitly indicated with a subscript because A is not a fixed matrix, it's an adaptive matrix. It depends on the input, but there is a matrix that describes this transformation, and then there's a constant that's being added. And this particular description of this network is valid over a region. Again, this is something that Rich talked about quite a bit yesterday. There's a region in the input space in which the activations are preserved. Right? So if I take any input, there's a small region around that input. In fact, it's quite small. There's a small region around that input, a neighborhood, in which all the activations don't change. I don't cross any threshold boundaries. And in that region, this matrix A sub y is the same. And it's computing, well, it's just a linear transform. And this B sub y, the additive component, the bias term, if you like, is also the same within that region. Okay, so what we did is we looked at the norm of the bias component. We wanted to know how much of the denoising is coming from the bias and how much is coming from the linear part. And we thought that a lot would be coming from the bias because of that idea of thresholding that I showed you earlier. When you want to build something like a soft threshold, what do? You basically do half-wave rectification twice, once for each side of the origin, and you want to do that after adding a constant to get your threshold. So we imagined that the way this thing operated, this deep neural network, was by computing soft thresholds again and again and again and again throughout the network. And that getting those biases must be really important to get those soft thresholds in place. So we wanted to understand a little bit about what the net bias of the entire network was if we analyzed it in this way. And it's very easy to do that. You basically calculate the Jacobian of the mapping. That gives you the linear part. And you can subtract that part out and get the bias. And you can measure, well, how big are those two things in terms of their contribution to the denoising? And the answer is that when you train over the whole range, essentially the entire job is being done by the linear part. It almost looks as if the training is trying to squeeze out the bias and set it to 0. Now, it's not quite 0, but it's small. So that's the observation. And the important part is that if you then go and look at a network, and by the way, I should have told you my my noise levels are now not expressed as PSNR, but as standard deviation. So everything is flipped from the previous plots. Sorry about that. But it makes it a little bit easier to understand what's going on. And this is now noise level in standard deviation against the norms of these components. And so what you can see is that when you train on only this half of these noise, the noise range, the bias is small as it is in the full training over the training range. But outside of the training range, the bias blows up. It sort of grows out of control. And that's not what it's supposed to do, at least not if you want performance like you had over on this left side. And sure enough, if you train over an even smaller region, it goes even more out of control. So we had a suspicion when we looked at this, that this means that the bias is basically overfitting. And it's overfitting to the training set, and it's preventing the generalization. So we did the most obvious thing, which is to eliminate the bias. Just get rid of it. And that's easy to do. These are just additive terms. So you just go through the entire network, and every time there's a linear convolution, you just keep the convolution output and you don't add any constants. There are no constants. You also don't put any in the batch normalization that's done during the training. So there's no constants at all, no additive constants in this network. It is completely linear. And so what happens, so the entire network is now linear, or adaptive linear, right? Because once again, it depends on the state of those activations, whether you're thresholding, it depends on the signs of the outputs, right? So all the positive value things are going to get through their rectifiers, and all the negative things are going to be thrown away. So there is that, but apart from that, it's linear. And that means that around every input vector, there's again a neighborhood, a little ball. It's actually a convex ball, and it's got facets that are hyperplanes. There's a convex ball of a region which has exactly the same linear transform. Again, that's what Rich was talking about yesterday. So, and amazingly, when you do this, it works. So up at the top is a noisy training image. We're going to train on things only up to sigma equals 10. And in fact, what you're looking at there is sigma equals 10. You can barely see the noise. There's a tiny bit of noise there. We're going to test on an image that has a huge amount of noise, sigma equals 90. Here's what happens when you try to denoise that with the standard DN-CNN, and here's what happens if you remove the bias. So you get rid of the bias, and now all of a sudden we can generalize over the training from a very small amount of noise in the training range up to something that has a gigantic amount of noise as in a test case, okay? So this succeeds, and just to emphasize it in plots, you can see what's going on. So on the left here is the blue is the bias-free version of this. Nothing else changed in the network, by the way. It's exactly the same network. We just removed all the constants. That's all. No other change in architecture, just no more constants. So it's an enormous difference. The red curve is just repeated from what I showed you before. That's the original DN-CNN with the bias terms. The blue curve is without the bias curves, without the bias terms, and there's a huge improvement. And generalization. So again, this is for training over very, very tiny amounts of noise. It generalizes to extremely large amounts of noise. It works for other training regimes. So if you train over some middle band of noise, so some range in the middle, you can see again that the BF-CNN doesn't generalize. It falls off in performance on either side, but this thing is managing to maintain it. And the same thing, even if you train only on high levels of noise, in terms of generalizing to low levels of noise, that works also. So in general, we get generalization, and that's a terrible phrase. In general, we get generalization if we get rid of the bias. The bias is basically hurting us. That's very strange and counterintuitive because it seemed like we needed the bias to do soft thresholding. So this thing is not doing soft thresholding, at least not the way we usually think of it. Okay. Here's another advantage of getting rid of the bias. Once you've gotten rid of the bias, now the thing acts linear. And you can analyze that linear function, and you can ask, okay, each pixel in the output, where does it come from? Well, it's just it's a weighted sum of the input. And what is that weighting? and you can actually interpret how this thing works. So here's a noisy image. Here's the denoised example. We're going to pick 3 pixels, and we're going to ask, how does each of these pixels get denoised? It's, again, a weighted sum of the noisy pixels. And here's the weighting. So here are the 3 weighting functions that are used for those 3 example pixels. This one down here has a weighting function that looks like this. This one has a weighting function that's kind of a little bit elongated. You can see also some little bits of red. Those are negative parts. And so it's not just a weighted, it's not just an average, it's got some negative parts. And over here is pixel number 3, it's a little blob up here. You can already see just from these 3 examples that those 3 filters, those 3 weighting functions are different. They're adaptive to the structure of the underlying image. They are not, this is not a convolution, it is not a Wiener filter. A Wiener filter would do a simple low pass convolution and do the same weighted sum everywhere. This thing is adapting to the content. And just to emphasize that a little bit more, let me show you, this was a small amount of noise. Here's more noise, and here's an extreme amount of noise. And look at what happens to these weighting functions. So they, first of all, they grow, as they would in a Wiener filter. When you have more and more noise, the Wiener filter becomes more and more low pass. It projects out or illuminates the high frequencies, and that means that the filter back in the spatial domain gets bigger and bigger and averages over bigger and bigger regions because it's trying to average out the noise. It's sort of obvious why it would do that. Here, the same thing is happening, but the averaging is specific to the content of the image. And I think the impressive things are things like this. So over here, you see that this thing is being denoised, this pixel is being denoised by taking a weighted average along this branch of the tree. This is a little chunk of tree, I think, tree branches. This one also extremely directional. And this one is a big blob down in the corner. So what you can see is the very simple point intuitively that this filter is extremely adaptive. It's adaptive both to the level of noise. It's the same function that's being applied to every single one of these. This F, the bias-free CNN is the same function, but it's adaptive to the context and to the noise. Okay, so, and now we can also do an analysis, again, because this thing is bias-free, we can just look at that as a linear transform, we can compute an SVD, and we can examine what are the properties of the SVD, what do the singular values look like, and here are singular value spectra across 9 different images, and what you can see is they're they fall very quickly. They essentially are doing a projection into a low dimensional space. So they're setting most of these axes to 0, and depending on the image, they're retaining a certain number of axes. The image content is basically going to determine how many axes are preserved. The noise level is also going to determine how many axes are preserved. So let me just show you a little bit about what the actual vectors, the singular vectors, look like. These are the V's. And in the high singular value region, the singular vectors look a lot like the image. So this is an example image, which is just a sort of a T-junction, if you like. And what you can see is that this thing has learned adaptively that that's the sort of underlying structure that it should try to preserve. Notice that these things are not like blurry versions of the original signal. They look they have sharp edges. They look like the T that we're actually trying to recover. It also seems to be partitioning off these different regions in a sort of interesting way. So here's something that looks like the original image approximately, and this thing is pulling off one region and this thing is pulling off the other region. If you look down here near the bottom, the singular vectors tend to look like noise. They seem to have no apparent relationship to the underlying original image. And there's further analyses that you can do, but I want to kind of move quickly to the next part of the talk, so I'm not going to go any further than what I just told you. Oh, here's one more example that's sort of interesting. So here's an example of digits, and these are high singular values, singular vectors, and that's a mouthful. So what you can see is that they look sort of like derivatives, spatial derivatives, and that's kind of an interesting idea, because if you wanted this thing to be translation invariant, that is to allow for translations of these structures and to say that I'm agnostic as to the position of these digits, but I want them to look like digits, then you might want to build in something that looks like spatial derivatives. And in fact, if you do things like calculate the spatial derivatives of the original image, the horizontal and vertical derivatives. Think of those as a Taylor approximation for translation. You can show that those derivative vectors, which are images, tend to lie in the preserved signal space. And so I don't have time to walk through that in detail, but that's just an observation. Okay, so let's say one more thing about properties of the signal space subspace before I go on. So you can sort of capture the effective dimensionality of this preserved subspace by just taking the mean squared error and divide it by sigma squared. If you were actually doing a projection onto a low dimensional space, this would be this, and you literally were taking that ball of noise and squeezing some dimensions out. The dimensionality could be estimated by just looking at the residual variance, the mean squared error, compared to the original variance. And the fraction that has been eliminated would be the fraction of dimensions that you've thrown out. So that's basically where this comes from, just intuitively. And you can calculate this by taking the expected value over noise samples of A times Z approximately, and then squared, and then dividing, so that's a vector norm of AZ, and dividing that by sigma squared. And that's just the sum of the squared singular values. Okay, so we have an easy way to sort of approximately estimate or describe the dimensionality if we want to think about this as a projection into a subspace. And the dimensionality is something that changes as you change the noise level. So these are empirical curves, the blue ones, for those 9 different images I showed you on the previous slide. And what you can see is that the effective dimensionality is falling rather dramatically with noise level. And you can basically fit these curves pretty well by just saying it's an inverse function. It's literally, D is roughly alpha divided by sigma, where it's a different alpha for different images, okay? And if that's true, you can actually go through a calculation. You can say, well, let's see, the mean squared error is let's see, if this is true, if D is alpha over sigma, plug that in up here for D and solve for mean squared error. That means the mean squared error must be going as alpha times sigma. And that's a little bit strange because mean squared error is a squared quantity. So you might think I made a typo and left out the squaring, but I didn't. And it turns out that the prediction then is that the PS, if you convert to log coordinates, the PSNR should go as something like the output PSNR should go as something like 1/2 of the input PSNR. And sure enough, up here, this black line is that function. It's basically a line of slope 1/2. And you can see that the CNN is approximately matching that line. Okay. So now we have kind of a bunch of properties that came out of analyzing this denoiser, and those were partly made possible by sort of forcing it to drop all the bias terms. That allowed both generalization, but it also allowed us to do all this analysis, doing an SVD, looking at singular values, looking at what's going on in terms of projections onto low dimensional spaces. And so all of this is described in this paper that we presented at ICLR this year, and there's a software implementation that includes 4 different bias-free CNNs and a whole bunch of examples, including replication of all the things that are in the paper, all the graphs that I just showed you, and some more. So if you want to know more, you can look that up online. Okay, so now I want to go forward to thinking about what does all this mean for the underlying prior, okay? And the observation is that there's something that I'm sure all of you have heard about. There's a manifold hypothesis for what image priors look like. Visual images lie on a low dimensional surface or a manifold because if you take any image and you deform it in various ways by translating, rotating, dilating, or squishing it a little bit, changing the light intensity, things like that, those are equally good or nearly equally good images in terms of their validity as natural images. And so the idea is that at least locally, we can think of this thing as a manifold. And we can think of those as being, let's say, equally probable. So the BF-CNN analysis that I just went through suggests that the tangents to this manifold are proper subspaces because there's no bias terms. If I take one of these tangents, it actually goes to the origin, and that the local subspace is determined adaptively by the binary settings of all those activations, and that the subspaces that we're talking about are continuously connected. And you can kind of work through the sort of math of what this deep net is doing, and those things basically have to be true. And that really suggests that the underlying geometry, the prior geometry that underlies the behavior of this denoiser is a set of facets that form the surface of a cone. And the facets correspond to those little activation regions again, that Rich was talking about. But the geometry of it is that it's a cone, a generalized cone, and it wiggles a lot. It has a very high curvature corresponding to, for example, high frequency information. So that's conceptually, I think, what's going on. And our question now is, can we use that prior for other problems? Okay. So what I'm going to show you from now on is how we go about doing that. So the first step is to go all the way back to the beginning, the formulation of the Beasley squares estimator. Remember, that's just the conditional mean. It's a well-known fact. Remember that the prior predictive density, P of y, is just a blurred version of the original of the prior. P of y is a blurred version of P of x. And now we're going to go through and derive something that actually was derived in 1961, but seems to have been forgotten. And it's a very beautiful and sort of bizarre result. And it's a paper by Miyasawa, who was looking at empirical Bayes interpretations and analyses of systems. And let me just show you what the derivation looks like, because it's actually really simple. So you take this prior predictive density, you take the gradient, and I'm not going to drag you through each step, but it's pretty straightforward to compute the gradient of this thing. You end up with this expression on the right. Now you multiply that by sigma squared and divide by P of y, and distributing that over the terms, swapping it with the integral and distributing it under the integral sign, we get that there's two terms. There's an integral of x times the conditional addition of P of x given y. And that, of course, is just our Bayes least squares estimator, the same thing that's at the top. You get a second term, which is the integral of y times P of x given y. And that's, of course, just y, because we're integrating against x here. Y comes out of the integral. This is just the integral of that density, which is 1. So flipping all of this around gives us the following. The Bayes least squares estimator is equal, this is not an approximation, is exactly equal to y plus a multiple of the gradient of the log of P of y. This is a very strange, I think, very strange formula, because remember the original formulation looked like, well, we had to calculate an integral. We had to multiply these two densities, and we had to take the product of that with x and compute the expectation, basically. So it's an integral formula. This is different. This is a gradient. So this is a gradient of the log of this density. And again, this is exactly correct. This is not an approximation. Assuming additive white Gaussian noise, this is exactly correct. And it turns out that there are formulas, related empirical Bayes formulas for many other noise processes. One of my students years ago, Martin Raffin, and I wrote a paper describing the generalization to many other families of corruption. But for now, let's just stick with additive white Gaussian noise. And this thing is, again, absolutely equivalent to the Bayes least squares estimator. It looks like a gradient descent expression, like you think, okay, it makes sense. I start from an observation y, and I go up the gradient of the density. That's what I want to do. I want to increase the probability of my observations. Starting from this noisy thing, I want to make it more probable. I want to make it more like an image. But this is not iterative. This is a one-step optimal denoiser, not something that you iterate. Nothing like that. This is not mean shift. This is not many other things that you've heard about or seen in the literature. This is a one-step optimal Bayes least squares estimate. The prior is implicit, but it's buried inside of P of y, because P of y is a blurred version of P of x. Okay. Here's a picture to maybe help you get your head around it. The green thing is a manifold, a wiggly one with variable wiggles, just to illustrate the behavior. The little red, the white thing is P of y. That's the blurry version of the green thing. Okay, so I literally put a constant probability mass on that infinitely thin manifold and blur it. This is a numerical simulation, but it doesn't matter. So the white thing underneath is the actual density, and the red lines, the red points are observed noisy observations, and the red lines show you what the Bayes least squares solution is. So each one of these gets corrected by going uphill on the white thing. Okay, move uphill according to the gradient of the white thing. And what you can see is that for large sigma, they often miss. They don't land on the manifold at all. In fact, look at this set over here. There's a big clump of wiggly green lines here that turns into a big white blob, and all of these guys are going partway up the hill, and they're not getting to the manifold. As you add smaller and smaller amounts of noise, these things converge to actually being projections onto the manifold, or they get closer and closer to being projections on the manifold, because the observations are closer and closer to the manifold, and you can basically, as you get close to the manifold, locally, it's approximated by a line, if you were in high dimensions, a hyperplane, and the Beasley squares denoising is just going to give a projection directly onto that line. Okay. So now we can think about using the denoiser. So we have a function that can compute this thing. That's our CNN, trained. Now we can think about using it to actually do something that's like, this is a diffusion process. The blurring of the prior is a diffusion process. So we can imagine doing something to undo the diffusion process by starting somewhere and going uphill and iterating. Again, the Beasley squares denoiser is not iterative. It is a one-step denoiser, but we're going to now use it iteratively. And we're going to essentially build something to go uphill on the gradient. As we do this, at each step, we're going to get closer to the manifold, so the effective noise will be smaller. And the denoiser knows that because it knows how to, it's a universal denoiser, it knows how to figure out how much noise is there. So we're going to rely on the denoiser to figure that out, and we're just going to let it take us uphill doing gradient descent. It's really, that's the core of what we're going to do. It's very, very simple. It's a course-defined optimization procedure because basically what you're doing is you're not doing gradient descent on a single function. Each time you take a step, you're going to modify your function to be basically another blurred version of the prior where the blurring is less. And as you get closer and closer to the manifold, the blurring gets less and less until you project onto the manifold. So that's the idea. The algorithm is very simple. It's what I just said, just do gradient descent. You can see in here, we're going to take a denoiser. X hat of y is our denoiser. That's our deep neural network. You just compute f of y, which is the denoiser minus y. It's the residual. And now you're just going to use the residual as your step, because again, we need x hat minus y to get the gradient, okay? So not only is this a very nice way to pull the gradient out of the denoiser, but it's kind of self-adaptive. It knows how to adjust its own step sizes as it gets closer and closer to the manifold, because it's a universal denoiser that's constantly estimating the noise. So there are many related things in the literature. I don't have time to talk about relationships of this to that. This is in a sense, a much simpler version, I think, than of using a denoiser to do iterative gradient descent types of solutions to arrive at a sample from the density. So let's look at how it works. Here's an animation on that manifold that I showed you before. And we're starting from various starting points, and we're going until we're following that, just taking small gradient steps until we get there. And what you can see on the right is an example of a whole bunch of trajectories starting at random positions and moving. They follow curved trajectories because each time we compute this gradient, it's a gradient, again, of a different function. It's a course-defined approximation of the manifold. Okay. Let me show you what it looks like when you apply it to an image. So on the left are two starting points. They're random starting points. And what you see is a sequence of images going as we ascend the gradient. And in each case, we end up with something that looks a little bit like a chunk of a natural image. It's got sharp edges, it's got contours, it's got curves, it's got dark regions, it's got light regions. And in fact, what's kind of cool is, first of all, notice that these two examples you get a totally different answer. And if you look at one of these and look at the features in it, so look at this thing, it's got a white blob in the corner and a little black thing underneath it, go all the way back to the starting point, and you can see just a trace of that in the noise sample. So these again are just white noise on the left, but they somehow, the algorithm is picking up subtle features that are buried in that white noise, building on them and pushing everything else out. So we get a lot of variety by drawing different samples from this, as I was trying to illustrate in the previous animation. Now we can enhance this algorithm by injecting some noise. And by injecting some noise, we're basically ascending this. We're doing gradient ascent. We're landing in a local optimum. And if we add a little bit of noise as we go, we can actually try to get to a higher probability optimum. And in fact, higher probability for images usually means smoother, and sure enough, that's what this is going to do, and I'll show you that in a second. So we're going to introduce another parameter, beta. The beta is going to control the amount of noise that's being added. We've done this. I don't have time to walk you through the derivation of the algorithm, but it's in the paper. The beta is very carefully chosen so as to control the ratio of the step sizes that are being controlled by the denoiser and the amount of noise that's being injected, and to keep those balanced and to allow convergence. And so here's a noisy, here I showed you. So let's try that again. There's the original trajectories I showed you. Here's with a little bit of noise added. Here's with quite a lot of noise added. In all of these cases, we get convergence, and I didn't show on here on these convergence plots. These are empirical convergence plots, but but the convergence actually seems to follow very closely the intended convergence that we've built into the algorithm. So we feel like this is we've got this really well under control in terms of achieving what we were aiming for. So now let me show you a few, here's some more examples. These are synthesized images with moderate amounts of injected noise, and on the right are synthesized images with a substantial amount of injected noise. And basically, my sense is that they all look pretty natural, but the ones on the right are generally smoother. They have larger blank regions or smooth regions. They have fewer contours, less details, less texture. Okay. Here's some examples from MNIST. So if you train your denoiser on MNIST, it learns a prior that's appropriate for MNIST, and you can go ahead and draw samples. If you add a little bit of noise, you end up in these local minima that still look like they're strokes of a pencil, a white pencil on a blackboard. If you add a little more noise, they become a little bit more digit-like, and if you add a lot of noise, they become much more digit-like. Okay. The last enhancement is we want to use this to solve linear inverse problems, deterministic linear inverse problems. So we're going to make a measurement with a matrix, multiply an original image by a matrix that is low rank. We're going to assume, just for simplicity, that this matrix has orthogonal columns. That's not necessary for the algorithm or for the computation, just makes it a little easier to work through the math and to implement. And we're going to introduce a modified version of our steps that are going to simultaneously take steps along the gradient and try to enforce this linear constraint. And so the idea is that we're going to end up with a linear inverse machine. So we're going to take this trained denoiser, which is trained using stochastic gradient descent. We're going to take the optimized theta out of that, and we're going to plug it, and it's got a training distribution that it's optimized for. And we're going to plug that into another circuit diagram, this is a circuit diagram for the algorithm I just showed you. And this algorithm is going to take a measurement, x sub c, from another image, and it's going to generate, fill in the blanks, fill in all the pieces that have been discarded by this low dimensional projection measurement. Okay, so let me if you're not used to circuit diagrams, this is probably not helping you, but that's okay. I just wanted to show you that you can kind of formulate the algorithm in a sort of diagrammatic form that actually makes a lot of sense, and I'm highlighting here where the parameters are. Okay, so here's what it looks like when you do this. The blue line is a linear constraint. The green thing is the same manifold I've been showing you. And now when you start from these random starting points, you end up at places that are intersections between the blue line and the green line, which is exactly what you want. You want to satisfy the blue constraint, and you want to draw something that's high probability from that manifold. Okay, so here are examples of real linear inverse problems. I'm just going to show you, I'm just going to blast through some examples to let you look at them. Here's an original image. Here's a missing pile of pixels. This is a linear inverse problem. It's a really simple linear inverse problem. We've just set a bunch of pixels to 0 or to, missing. The measurement matrix in this case is basically just has in each of its columns a 1 at each of the locations of the pixels that we're keeping. Here are 3 restorations. This is stochastic linear inverse. So we're going to, from different starting points, we're going to end up at different solutions. Here are 3 solutions. They all have the same bordering pixels, but the middle has been filled in. And notice that it's been filled in very different ways. None of them got the original back. but we didn't expect them to. I mean, if I showed you this thing with the black square missing in the middle, you wouldn't know what to put in the middle. And neither does the algorithm. But it does three things that I think are pretty sensible, pretty plausible. Here are additional examples. You can see down at the bottom, the original image is at the top, the missing square is shown in the middle, and the restored images are shown at the bottom. You can see that, again, it's not like it gets the right answer, because it can't, but it produces something that looks quite plausible, fairly seamless, and natural. I think you would be hard pressed to say where were the missing pixels in most of these. If I were to give you that task as a human, can you find the location where the missing pixel box was? I think it would be difficult. Here's another example. We're going to now just drop random pixels. So here in the left three examples, we're going to keep 30%, drop 70%. So these are the retained pixels, and this is the recovered images at the bottom. They look remarkably good. You can see they've lost a little bit of detail, some of the very fine texture, but they look remarkably good. Here it is with only preserving 10% of the pixels, and now I think you can really start to see differences from the originals, but I still think the results are pretty remarkable. Here's another one. And by the way, every single one of these applications, every single example is computed with exactly the same algorithm. The only thing that's changing is the matrix M, the measurement matrix, because we're, of course, measuring a different linear space each time. Otherwise, it's exactly the same algorithm, same parameters. So here's another example. Here we're doing 4x4 block averaging. So we take this image, and here's the block averaged version, and then we recover that. So this is a kind of a super resolution problem. And you can see that that's working pretty well. Here's a blurring problem. So now we're going to discard the high frequencies. It's a different kind of super resolution, if you like. And you can see that that one works pretty well. Here we're only keeping 10% of the low frequencies. And the last one is probably the most interesting for this crowd. This is random projection. So we're doing the compressed sensing problem. We're going to take, let's do the right ones, the 10% projection. So on the left of the red line are 30%, on the right are 10%. So each of these images we're going to project onto a random measurement basis. If we try to reconstruct just doing the sort of obvious pseudo inverse, we get garbage. You can't really see anything. If you recover using our method, you get these three images shown here, and the numbers underneath are giving you the PSNR and the SSIM, perceptual quality metric. Underneath that are what happens if you do a more traditional compressed sensing recovery, assuming either sparsity in the DCT or sparsity in a wavelet representation. And what you can see is basically the prior that's embedded in this neural network, the denoising neural network, is really much, much better than the sparsity priors that we typically use, the union of subspace priors that we use in these DCT or wavelet sparse representations. Okay, that's it. That's what I wanted to show you. We are very interested in understanding how the CNN is achieving these adaptive projections. That's actually still mysterious. I didn't explain to you how that happens, and we don't really know. In fact, it's doubly mysterious because, as I told you earlier, achieving something like a thresholding, like a soft threshold, is not something you can do once you eliminate the biases. So we don't really understand how it is that it's doing what it's doing. We're interested in improving the denoising by modifying the architecture. We want to understand how we can modify the architecture to be more appropriate, given, for example, the sort of cone geometry of the prior that we think we're finding. And we're currently working to generalize this to other inverse problems, including nonlinear measurements and stochastic measurements. And this work is, it's on the archive, and it's going to be in a workshop at NeurIPS. And I want to thank my collaborators, Zara, Sreyas, and Carlos, and my funders. And I'll stop and take questions if we have time. I guess we don't really, because I'm a few minutes over my hour.
Thank you so much, Eero. Yes, your talk was great, but we don't have time to do the questions right now. But if you look at the Q&A box, there are some questions that maybe you can answer by text.